I'm Andy Brush of TGAM, and as you can see, I'm sitting in front of a pile of RF calibration equipment, and our goal today is to demonstrate how you can use some of this equipment to calibrate through-line watt meters of the more automatic communication-oriented variety, but also we're going to demonstrate calibration of a nice old manual clunker here. Okay. So when you're calibrating diode detectors, all the manufacturers tell you use very low harmonic content energy. And when you're buying a Class A amplifier, you're hard-pressed to find an amplifier vendor who's going to guarantee better than 20 dB harmonics or minus 20 dBc harmonics. So the harmonics have to be filtered out. So the main element is an 8-way switch. There's 8 low-pass filters in each of these 3 chassis. Each low-pass filter covers a band. And for example, a band might be 1 megahertz to 1.6 megahertz. It might be 1.6 megahertz to 2.5 megahertz. The bands are all going to go up in ratios like that of about 2/3 of an octave. Because amplifiers don't necessarily come in the same bands that filters do, we have the 1322A that independently lets you route the signal from the low power signal generator to 3 amplifiers, and then having got the high power signal back from one of the 3 amplifiers, can then route it to one of 3 chassis of filters. And which relays are selected here are determined by our 1320A relay driver box that's receiving a bit pattern from the software. So let's start with the calorimeters. Here, this item here is a TGAM model 1314 250 watt calorimeter. It's useful from 50 hertz to 3.5 gigahertz at least. It's at reduced uncertainty, at increased uncertainty, I think it's still tolerably useful up to about 4 gigahertz. Right here, we have a 5,000 watt calorimeter, TGAM model 1315. This might be the only such calorimeter we're ever going to build, and you'll see why in a minute. This is useful from 50 hertz to 500 megahertz, and it's 5,000 watts. So now let's have a peek at the model 1316. This is the 1316A calorimeter. This calorimeter is 10,000 watts, 50 hertz to 1 gigahertz, and has lower uncertainty than the 1315. So this is becoming a production product, whereas the 1315 did not. And connected to the 1316 is a TGAM model, that's a 5540. And maybe it's more fun to look at one whose display is lit up. So here in a package that's roughly the same size as many familiar through-line watt meters, we have not only the through-line sensor, and this is a sensor that at its calibration points is accurate within 1% or better, but it also includes the meter and the display. So you get forward power, reverse power, frequency, and the VISWR right on the unit for diagnostic purposes. And because you do want to communicate with it, it's a simple USB interface. So for our first task, we're gonna test this bird sensor, get a cal report for it. So let's go look at the software that's going to run that. We're going to use the software HPC SW. And let's see. I need to move this over a little bit. So to get the software going, the first thing I'm going to do is just make sure that I have all my instruments attached to it. So my TGAM 1830A, it's connected over Ethernet. I've checked it already, but I can read it. Get some answers that are very low because there's no power on right now. I'll check the RF power meter. It's been checked, it's connected. It read a serial number from the sensor. You can check the sensor, it's a 4021. Everything good to go. I can read the sensor calibration data out of it. Make sure it has all the points we need in it. Sometimes this takes a second to do. So this sensor is calibrated from 1.8 megahertz to 32 megahertz. What else do I need to look at? I've got my generator connected. It's a Roden Schwartz. I've got the drivers for it loaded. So now we need to define our test. We put in some record keeping information like my initials, the temperature, the test ID, but most importantly, what power do we want to calibrate at? I'm going to do a test today at 100 watts. The test limit's plus or minus 3 watts. That's because the Bird 4421 is a 3% sensor. And let's go over here to the read the sensor data button and populate the frequency list. So we've sent a query to the power meter to ask the sensor what its frequency data is. You see we've got 14 points out of a possible 21 that are in the sensor. Now it takes several minutes to test each of these points. So what I'm going to do is I'm going to clear this list and then just type back in 3 of them for the sake of illustration. So I'll pick a low one, a medium one, and a high one. We can pick frequencies by pulling down the list of predefined frequencies. And we'll just add, let's say, 2 and 13 and maybe 25 megahertz. Now there's 2 kinds of tests we can do on this sensor. We can calibrate it or we can adjust it. And we'll go ahead and adjust this sensor today. I'll go from the fast calibration button, click the adjustment test button, and the main difference that does is it illuminates these check marks over here for burn, which is essentially program the EEPROM in the sensor. And we'll do that at 100 watts. Let's see, the pass fail, I have the verification is going to be 3%. So I'm going to go ahead and start an automatic test and then walk you through what's going on while that happens. So click the start the test button. First thing it asks is, do you want to erase the calibration memory in the sensor? You have to do that if you're going to realign it. And yes, that is risky. And yes, I do have a backup copy of the data that I can write back in case anything goes wrong. In fact, well, when the test is over, I'll show you where that button is. So we've erased the calibration data. So I need to connect, enable, and set gain on all amplifiers being used. Well, in this sensor, I have 1 amplifier that covers the whole frequency range. But if I needed to use some of the other amplifiers, the TGAM RF power switch 1322 selection matrix would switch us back and forth between the amplifiers under automatic control. My amplifier is on and it is set to an appropriate gain. And it says, do you want to do the test at 100 watt level? Yes, I do. The first thing we're doing is we're zeroing the meter that is connected to the thermistor sensor here. It's always a good idea to zero thermistor meters right before you're going to use them. All right, so we've set the filter bank for the 25 megahertz filter. And that's because we're starting at the high end of the frequency range. We've set minus 20 dBm, and that should result in a watt or two. The software is being conservative and finding out what the gain of the amplifier is before it really goes ahead and lays the power on. And it's set a 1-minute timer to let all the power meters settle. And again, that's a bit conservative. We'll just have to wait for that timer to tick down. When the timer is timed out, it's going to calculate a new signal generator setting and keep at that until we're within this limit here, 0.3 of a dB of the 100-watt set point. Sometimes that takes a couple iterations to get there. While we're waiting, I'll point out that we're using one of our calibrators here. The calorimeter makes a fine water-cooled load. The calorimeter is already indicating 1.35 watts. But the reason we're using the coupler is the calorimeter takes about 6 or 7 minutes to give you a fully settled reading. And you get a fully settled reading from the coupler really within 15 to 20 seconds. It's maybe a little bit too conservative to wait a whole minute. All right, so the signal generator has been adjusted now to based on the gain computed from the 1.3 watts that was read. So we've got another minute to wait while everything settles, and then we'll probably be right around 100 watts. Now you can also see that as this test proceeds, I don't have to do anything. So even if we wanted to burn all of the 14 points that this power sensor really needs, it's a hands-off job. You start the test, walk away, and come back when it's finished. There we go. It says leveling criteria was met. Now in 15 seconds, we're going to go ahead and send the command to burn the EEPROM of the bird. And then as soon as that's set, we'll go ahead and read it back and just verify that that point was burned correctly, and then write the yellow line of the test report. There we go. So we did the 25 megahertz right of the EEPROM. We turned around, read the meter back, and unsurprisingly, there was only 50 milliwatts difference at 100 watts, because that's a brand new calibration, had not had a chance to drift or really do anything wrong yet. The system switches to 13 megahertz. Among other things that it did, as soon as it set the generator to 13 megahertz, it chose a new path through the low-pass filter system. We'll talk a little bit about this filter bank while the system's leveling. In each one of these chassis, there are 8 sets of low-pass filters that cover 3/4 of an octave. They have a very steep roll-off above their breakpoint, so we're effectively filtering out at least second through 7th harmonic with at least 30 dB of cut. So,
Dan, can you stop screen sharing for a bit while you talk about the equipment?
I could. Okay. Okay. So with 30 dB of cut on the harmonics and amplifiers that are all being operated in the range where they will produce less than 20 dB of harmonics, we're putting less than 50 dB C harmonic content into the sensor, which is appropriate because both of these types of sensors are diode detectors, so effectively peak voltage indicators, and any harmonics could distort the wave shape and give a very incorrect power reading. So the low-pass filter banks and amplifier selector are all driven by the software that contains a lookup table to know what path to select to connect the right amplifier and the right filter for the testing being done. So we got the system adjusted to close enough to 100 watts, and we're about to do that point's burn. So what's happening here is, let's look at this line really quick. Right before it's sent the average power measurement to the bird power meter to make the cause the calibration, it took these 4 points, computed their standard deviation, and compared that with a criteria that I'd set in this window. And that's essentially to make sure that the system is leveled well enough that it's appropriate to use that average. If for some reason, let's say it was an amp whose gain changes substantially as its temperature warms up, or maybe one of the filters gains or insertion loss changes as it warms up. Sometimes you have to wait a few minutes to stabilize the power well enough to use it for calibration. And this check makes sure that you don't accept. Sometimes you'll see it collecting a new set of data saying a standard deviation was too high. I'm going to add a few more points to the list and wait till everything is stable. All right, so we've passed and moved on to the 2 megahertz point. We have about another minute to wait, and then it'll go ahead and use that point. The bandpass filter bank that I was talking about with the 3 chassis of 8 filters apiece, we're doing bandpass filtering over a range of 100 kilohertz to 4.2 gigahertz, which is probably a wider range than most people's labs need. But our lab covers that range because we actually calibrate products over that whole range. Many other labs might only need 2 sets of 8 filters to cover their needed range. All right, we're leveled out at 2 megahertz now and about to get the point burned. Okay, we passed the standard deviation criteria, so it's going to go ahead and send the average on the bird and tell it to do the calibration job. Okay, so went ahead and did that. The test is completed. Okay, out of that, and then let's take a look at the log file that was generated. All the intermediate readings that were made are captured in the log, but at the end of the log, we get a little summary here of the lab conditions, the operator's initials, what the standards, model number, and serial number were. Oops, I'll scroll right there. We go. All right, so there's all the record of the tests we did, and this part here is suitable for cutting and pasting into a report, putting the frequencies, and this part here for these bird sensors that have their own built-in frequency meter is a good check of that. No provision is made for adjusting that because it's really just a counter, but you do want to check that it's reading right. So that's that. The sensor is now ready to go with its new calibration constants. And there's the report. In the event that you wanted to verify that the cal worked, you could come back to your application, switch it from an adjustment test to a fast calibration test, and it would just repeat that whole thing without burning the EEPROM. And I'm not going to do that because it's so time consuming and it looks just like what you just saw. So let's not go there. Okay. Checking for questions. All right, so let's see what it's like calibrating a manual meter. I mean, it's really a lot like calibrating an automatic meter. But so the first thing I want to do is turn my bird meter off and get this guy out of the way. I should look over at the signal generator and make sure it's turned off. That's always a good thing to do before disconnecting RF connectors. So the key difference between this meter and this meter is we can't ask this meter what its power reading is. So what we're going to see is the software provides us a few facilities for letting the software know what the reading of this meter is. So there's a couple very minor setup changes we have to make. We need to go to the RF power meter, and we need to close our connection with it. And then we need to go to the manual cal tab and say, let's do this in manual mode. And then we need to pick some appropriate frequencies to test that meter at. And 2 megahertz is not one of those. I think we should test that meter at 150 megahertz, and I think we should test that meter at 477 megahertz. And more than that, I think would just get redundant. So let's go back to the test info. Yeah, we're going to test it at 100 watts. We are going to use that amplifier. We have to use that amplifier. Using the same coupler, so I can use the same coupler coefficients. I'm using the same 1830A. Filters are all good. I'm not going to try to adjust that because I can't adjust it electronically. Pass criteria on the telewave is 5%. And other than that, I think we're good to go. Let's start the test. There it is. Is that box displaying on the shared? Okay, great. All right, so I could use these controls to raise and lower the generator by a dB, a tenth of a dB, or a hundredth of a dB to get the needle perfectly aligned with the scale to reduce uncertainty. In this case, I'm just going to read the number off the scale and type it in. And about what I think it is. Okay, I read about 96 watts. So I'll type 96 in, hit return. It says that the 1806 in the coupler, we're indicating almost 99 watts, so we're off by 3 watts or so, which is 57% of the test limit, so the unit passes. And in the meantime, while I've been talking, went ahead and zeroed the 1830, set the switches for 477 megahertz, and it also rerouted the power. So over here, the big amp is done at 225 megahertz. So we had to send commands to the signal router to bring this amplifier here into play, all automatic. All right, test finished up. We can see that we're at 158% of the test limit at 477 megahertz, so we had to fail a unit. Log got created. Here it still has the same stupid scrolling problem. But there's the information block at the end that you can cut and paste and use in a report. There's a couple other features of this software that I might want to point out, and one of them is if you're calibrating a sensor that has cal tables for forward and reverse, to calibrate it in reverse, you merely install it in reverse and then come in here and click the button and say, I'm measuring reverse power. and I'm going to say no here because I don't want to cause anything to happen to a sensor that's not even connected. But it's that easy to calibrate one using forward and reverse. You just run a full set this way, turn it around, run a full set that way. Likewise, if you want to calibrate the telewave in reverse, obviously turn the switch to reverse, then you flip it around. Moving to the coupler and thermistor-based units as transfer standards, and that's what we use today as a transfer standard. This particular one is a TGAM model 2601A. It covers 100 kilohertz to a gigahertz with full power of 250 watts. And that would make its good uncertainty range between, it's about 100 to 1 power range, so maybe 2.5 to 3 watts to 250 watts. The 5540A has very good accuracy, and depending on the level of calibration file and whether this was calibrated on a calorimeter or on a transfer standard, these can also be useful as transfer standards. The 5540A is nominally useful from 3 watts to 10 kilowatts, from 200 kilohertz to 200 megahertz. There is another member of the family in the pipeline that is 300 milliwatts to 1 kilowatt, 1 megahertz to a gigahertz. And then their accuracy at a calibrated point is always better than 1%, closer to 0.5%, I think. And then accuracy between points really depends on the calibration that was ordered. If calibration frequencies and powers are far apart, maybe we get outside 1% between points. If the calibration table is fully populated with an extensive test, then better than 1% across the board. We have a question. Does the software also have a routine built in to calibrate the calorimeter itself? And the answer is yes. Well, it's actually different software. The calorimeter is calibrated by precisely measured 60 hertz power. So you take a very well-leveled, regulated sine wave source, pass it through a revenue grade mains power meter into the calorimeter, and you essentially are calibrating the power linearity of the calorimeter. And we have a piece of software called HPC Cal that fully automates that into a hands-off process that then goes ahead and produces the cal table for the calorimeter. This software, the HPC SW that I showed you, has a routine for using the calorimeter to calibrate a transfer standard. So I was in today fast cal mode, which uses a transfer standard. I could have in let's call it regular mode, I could have put the device under test right onto the input of the calorimeter. Now, for example, right there, and I've then done a more time-consuming but lower uncertainty calibration using the calorimeter driven by HPCSW. Then HPCSW actually was used to create the coupler calibration factors that we imported today. Great. Well, thanks again.